Okay, thank you very much to the organizers for the invitation to speak at this great conference. Just wanted to make sure, just some checks. Is this large enough for people in the back? Okay, good. Let me know if my writing gets a little smaller as it goes. So right off the bat, this is joint work in progress with John Pardon and Vivek Shende. What I'd like to do is give you first an idea of the picture we have in mind and what results we have, including where we're hoping to go, what's in progress, and so on. Okay, so let me just introduce the question. So we start with a Weinstein manifold. Okay, meaning that, I won't recall the entire definition, but of course this is a Liouville manifold equipped with a compatible Morse function, compatible with the Liouville vector field. And when we have such a thing, we can associate to this data of a Weinstein structure an object L, which I'll call the skeleton of X. And if you want, concretely, it's simply the union of descending manifolds of this function phi. And a basic property of Weinstein manifolds is all of the critical points have index less than or equal to n, and their descending manifolds are all isotropic. So these are all isotropic, and L, we might call it a singular Lagrangian spine of X. Okay, it might just be isotropic. In general, we'll just call it a singular Lagrangian spine, even if it's only isotropic. Okay, and so there's a conjecture due to Kontsevich in something like 2008, that this spine, together with some data, should know entirely about the wrapped Fukaya category of the Weinstein manifold. So let me formulate the conjecture a little bit vaguely. The wrapped Fukaya category of X should be equivalent in some sense to global sections over this Lagrangian spine of a cosheaf of categories defined on the spine. It should be a constructible cosheaf, but I won't say that word there. And equivalent in some, derived equivalent, Morita equivalent. I don't want to, again, be precise about that. So there's some statement like this, which, you may look at the statement and say, what good does it do to us if we knew this? There are some things I might add to that statement that make this potentially a computational tool. So also, and these were basically stated at the same time as the conjecture. You would expect in ideally, or in nice cases, if you look at sections over small open sets or local stocks, of this cosheaf, they should be simple or combinatorial in nice cases. Okay, so we have this wrapped Fukaya category where, yes, question?
I'm being too ignorant and not listening back in genre, but I thought that the Fukaya category was not supposed to be a local object. So how can this be described?
Yeah, so this is a great question. I think one point is here we're looking at a Weinstein manifold, which is like a Stein manifold or an affine variety. So it's an exact symplectic manifold. So you expect somehow there are no disks, that big disks. There are small disks, but now the intuitive argument that might make you believe this to be true is you can essentially, this retraction onto the spine is basically a symplectic retraction for large time. So you can sort of compress everything to a very small neighborhood of the spine, and then you might start to expect something. But I would say still it's surprising to me. Other questions about the statement? I mean, okay, so there should be some simple local forms. So, the first examples of stocks given, if you haven't seen this before. Let's say you're, let's say you're at a smooth point of the skeleton. Okay, then there's nothing to do. So here's a point P. The stock should just be, if you want, this trivial category, one object, identity endomorphism. So okay, or K. Okay. More interesting if you start to look at singularities at which there's no manifold structure, some tripod type singularity. And here, the proposal, already going back to Conceivage for what the stock should be, is it should be some fundamental exact triangle category, meaning there are three objects with morphisms like this, but they form an exact triangle, so successive compositions are 0. There's a mu3. Okay, so I can just write that as some sort of module category over this thing. Okay. Great. Okay, so these are some examples, and I would say a big breakthrough in the geometry of what should be going on comes from work of Nadler in 2013. So there are some models of these sort of basic singularities, this and multi-spoked wheels in low dimensions, but Nadler proposed a class of singularities in all dimensions. Okay, so he proposed a combinatorial class, or nice class, of singularities of Lagrangian skeleta in all dimensions. Which he called arboreal singularities. And today, what I want to describe is some work in progress, which is for the case that singularities are nice. So let me say it this way: work in progress towards realizing the conjecture when the singularities of L are nice, for instance, arboreal. You might imagine there's a larger class of nice singularities. For instance, the n-spoked wheel in this one-dimensional case, but let's just restrict to arboreal singularities. And maybe I should just add that one might wonder how much of a restriction this is in terms of what types of manifolds we can get. And the expectation, due to work of Nadler that's already out and ongoing work of Eliashberg, Nadler, Starkston, is that actually you might be able to use the case of arboreal singularities to get at the completely general case, because arboreal singularities are somehow generic singularities in the space of skeleta of Weinstein manifolds. Okay? So the expectation is that arboreal singularities are generic in the space of singularities of Weinstein skeleta, okay, on a fixed Weinstein manifold. Something like that. Okay. So they have work in progress that says that if you, so Nadler proved on his own that if you have an abstract Lagrangian Legendrian, you can deform it. And now there's a question about deforming the vector field, and the Weinstein data near it. And we might hope this to be true, in which case you could use this to get at more general classes of singularities. Okay, so what I'll talk about today is mostly phase one of the project. It's a multi-step project, but I'll sort of say a few words, at least now, about what's next, and maybe later if there's more time. So phase one, to understand this, if you want to think about what sort of co-sheaf of categories has global sections, the wrap category, the proposal already is these should be like local Fukaya categories associated to an open set on the skeleton. So you want to make that precise, and to do that, you should understand what sort of symplectic geometry is associated to an open set on the skeleton. Okay, and so we have a notion of a well, let me just say it this way. So we developed some local to global symplectic geometry. In particular, there's the notion of a Liouville sector that I want to describe and spend some time on. In this talk, it's a generalization of a Liouville manifold, but Liouville manifolds tend to admit nice coverings by Liouville sectors. So I want to talk about that and the local to global symplectic geometry, in the geometric sense, but also the local wrapped Fukaya categories. And what I might call the pre-co-sheaf structure. So anytime I have an inclusion, I have a push-forward map. So the main result I want to talk about today is a local to global generation theorem. Okay, so I'll state the theorem now, and then I'll elaborate upon it later. So the theorem is as follows. So for a homological cover, of X by Liouville sectors, which are nice. So each individual sector should be nice, meaning, well, I'll say what I mean when we get there, but something about having enough Lagrangians, something about some sort of open-closed map. Okay, so if I have a covering by sectors which are nice, then I actually know how to generate the whole wrapped Fukaya category. So the statement is that then the wrapped Fukaya category of X is generated by objects in the wrapped Fukaya categories of the pieces. Okay, so this is the first thing you might want to prove, because if you hope to establish a statement like this, you have to come to grips with the fact that there are large Lagrangians that may not be in any small piece of your symplectic manifold. Okay, so I might recap this as saying, well, I have some, this cover gives me some sort of diagram of categories. If I take some sort of colimit of this diagram, that the image split generates. Which is saying that if I look at the associated maps on 12 pi's, this is essentially surjective. Okay, so I hit everything. Okay, so that's, any questions about the stated results? Yes?
Can you describe in Cauchy's conjecture what the Cauchy categories for Cauchy model?
Great. That's the next example I have to say. So let's warm up with a cotangent bundle. But other questions first? Okay. Sorry? Wait, sorry. What if the category you were starting with was partially wrapped? Yeah, we believe we know the statement there too. There's a question about what the generation criterion is for a partially wrapped category, and there are a couple different ones. And so it's, I think what we're showing here has all the information, but there's some Fleury theory to think about. Yes?
Do you know mirror interpretation for label sectors?
I didn't think about it, so I'm not sure.
Can you say one word about homological covering?
Yes. Okay. Basically, we cover X by some sets, and we want to know that if we look at the cochains of each of these sets, or some sort of homology groups of each of them, and well, imagine just it's a decomposition into two. We might want to know that we hit every homology class here by looking at all the homology groups here and all the maps between them, and we build some big complex that thing maps to the homology of X. We might want to know we hit all of the homology of X. I can be more precise when we get there. Okay, so one word about phase 1.5. So the next thing to say is that arboreal singularities should induce something, Liouville sectors, which are nice in this sense. Okay, so for each singularity, you should be able to define a sector, which is nice in whatever sense I meant here, having enough Lagrangians. And so now you can consider coverings by arboreal sectors, whatever they are, and apply this result. And finally, phase 2, which is maybe the furthest out, is that there's this map, and star is cohomologically full and faithful. Okay. So this map, in nice cases, is really a derived equivalence. So I'll just say the Cauchy property, as opposed to pre-Cauchy. Okay. So before I go into any more detail about that, let's indeed do an example. So let's look at the cotangent bundle of a spin-oriented manifold. Okay, and what sort of situation are we talking about? So the associated Lagrangian spine, you can just choose to be the zero section. And, well, we know we have a topological model here for the wrapped Fukaya category. So we know that theorem of Abu-Zaid's tells us that, I'm going to say this in an unconventional way. I would say, well, not unconventional, but not the most usual way. So, you might say the wrapped Fukaya category is Morita equivalent to chains on the base loop space, or sort of, equivalent on to apply categories. I'll say it's Morita equivalent to the path category of Q. Okay, so this is the path category. This is basically the same information as chains on the base loop space, but it just has more objects. So the objects are points, and the morphisms. I don't know if this is true, so I'll just are chains on path spaces between the points. Okay, and I compose morphisms by composing paths. I'm looking at the induced map on chain complexes. Okay, so here the claim is this is the global sections of a co-sheaf of categories on the skeleton. So, so what is the co-sheaf? Well, what do we associate to an open set U and Q? Okay, well, there's a natural thing you can do, which is just take the path category of U, right? Okay, so you associate the path category of U. Objects are points in U. Morphisms are paths in U. And note that there's a natural. Whenever U is contained in V, I can include paths in U into paths in V. Okay, I can include the points and I can include the paths. Okay, and it's known that essentially if I take a nice cover, I think I need to. So if I take a nice cover, that actually the colimit of these categories is homotopic colimit is that this is a version of Van-Kampen's theorem. Okay, so we might think that if there were no higher homology of path spaces, these are just fundamental groups, or this is the fundamental groupoid, and this is saying that I can compute the fundamental groupoid in Q by cutting up any path into small paths adapted to an open cover. Okay, so this is a version of Seifert Van Kampen. Yeah. Questions?
I don't know if this matters for your later proof, but since Q is a manifold, you don't need the niceness.
Okay, great. Well, that's good to know. Yeah, I don't think it matters for what I'll say today. Thanks, though. Yeah. Okay, so what we need is a way to talk about. So it seems like we should be looking at open sets along this skeleton and looking at symplectic manifolds associated to them. And the natural thing you can do is take the cotangent bundle of the open set. Okay, so that's the sort of thing a Liouville sector is. Okay. A Liouville sector X is a Liouville manifold. Okay, so importantly, just to keep things simple, we're talking about the completed Liouville manifolds, not Liouville domains. This is this is completed. So it's a Liouville manifold with boundary. Okay, so it has some boundary, it has some completed part too. This is modeled at infinity on the symplectization of what I'll call the boundary infinity. So this is a contact manifold with boundary. Okay, so it's but that's not what a Liouville sector is. It satisfies an additional condition. And that condition is very important, so let me state that now. And then we'll do some examples. Okay. Satisfying the following condition, there exists a Hamiltonian vector field xh, well, let's xi, using, so there's a Hamiltonian vector field near the boundary, based, using a Hamiltonian which is linear at infinity, okay, which is transverse to the boundary. Okay, so I can find some Hamiltonian defined on the boundary, or some open setter on the boundary, such that the associated Hamiltonian vector field is transverse to the boundary everywhere. Okay. Equivalently, there's this function I from the boundary of the symplectic manifold to R, satisfying the following. So it's linear near infinity again. Okay, just meaning di of z equals I. And satisfying the following condition, if I take di and I restrict it to the characteristic foliation of the boundary of this symplectic manifold. So remember, it's the boundary of a symplectic manifold. It has this characteristic foliation. Yes?
Is the only piece of boundary you have the one that comes from the boundary of the contact manifold times R?
Yeah, and that extended to the interior, exactly. So
The other pieces of boundary just floating around in the interior.
yes, well, let me just do like the simplest example. Okay, so so here's the definition. Indeed, so the only piece of boundary is the thing that near infinity is the symplectization of the boundary of the contact manifold. Okay, so this is some technical condition, but I just want to point out that there's a very simple example which this immediately shows as a Liouville sector. Okay, so so let's do T star of a manifold where M is a manifold with boundary. Okay, so for instance, the closed ball. Okay, so before I said I want to understand the cotangent bundle of an open set, but I think just it's convenient to look at the cotangent bundle of the closed ball just to understand the boundary structure. Okay, so we look at this. Let me just do the simplest example here. So here's T star of 0, 1. Okay, and so I need a function defined near the boundary, and I get a function defined near the boundary by choosing an inward pointing normal vector. Okay, so I choose, so we get I. Defined on the boundary of, so this is x. The boundary of x is the cotangent bundle of M restricted to the boundary. And so I get a map from this thing to R. by looking at I take some vector field that's inward pointing, and I pair with it, and I get a map to R. Okay. So all I'm well. What should I say? Any questions about that first? Yes. Yes. Great. So absolutely. So indeed. So if you look at the canonical orientation of the characteristic foliation, it's increasing and decreasing, right? So indeed. So I have a function that's supposed to go to positive infinity on the right side and negative infinity on the left side. I think it's based on you choose a convention. Okay, so there's this boundary, and it has some sort of special form. It has this sort of, this transverse vector field that happens to be linear. It arises in nature, and it gives us lots of control over holomorphic disks. That's what I would say. Let me give a couple more examples of Liouville sectors. So okay, trivial example, any Liouville manifold, boundary is empty. Now if I have here's another source of Liouville sectors. Let's say I have a Liouville sector, such as a Liouville manifold or one of these, and I have some additional information. So I have a Liouville hypersurface in the boundary at infinity. Okay. So this is a stop in the sense of Sylvan. So let's say I have a Liouville sector and some sort of hypersurface at infinity. What I can do is I can remove a neighborhood of that hypersurface and get a Liouville sector. So what I can do, the claim is that x minus some neighborhood of this fiber, meaning in Zach's notation, the image of something like the fiber across the half plane. And I get a sector. Okay, so if I have here's a picture of that. Let's take the ball with its standard Liouville vector field. Okay, and let's say I have a stop that looks something like this, near infinity. Okay, so what I'm supposed to do? Oh, so actually maybe I want to I'm going to denote the boundary at infinity by dotted lines to distinguish it from actual boundary. Okay, so what I do is essentially I take neighborhoods of these things and I take a bite out of the apple. Okay, so what I do is I look at the following. Okay, so here's so this was my original Liouville manifold, and here is my new Liouville manifold. I've removed some neighborhoods like this. Is there a question? Okay, so this notion of a Liouville sector, I mean, it's very closely tied to the notion of a stop. I mean, it's essentially the complement of a stop. In some sense, it's nearly equivalent data, except for some purposes, the sector perspective is useful. So, for instance, if you're covering something by Liouville sectors, you don't see, how stops of small things interact, at least in some cases, except in some cases. So, okay, so let me tell you about local wrapped Fukaya categories if there aren't any other questions. Okay, so now we'll just look at a Liouville sector. I want to associate to it a wrapped Fukaya category. Its objects are going to be properly embedded Lagrangians. Okay, so they're allowed to be non-compact, but they're properly embedded, so our sector has some boundary that means that they stay away from the boundary. Okay, so they're away from the boundary. So an example of a Lagrangian we might like is something like that. Okay, and Hom well, let me just tell you about the cohomology of Hom. So Hom, cohomologically, well, as usual, wrapped Floer homology, you can think of it as some sort of limit of, Floer homology groups where I flow the first Lagrangian and then test it with the second Lagrangian, and now take the limit over some sort of increasing sequence of increasingly positive Hamiltonians. Okay, so H linear, so you look at linear Hamiltonians, but there's an important restriction. Is that they should be cut off. Okay, so you don't allow your Hamiltonian to wrap you past, okay, your boundary. So maybe I can draw a picture of the flow of such a Hamiltonian in some cases. Okay, so here's T star 0, 1. Here's the boundary of my sector. Okay, so what I do is, well, ordinarily a linear flow would be a flow that way and that way, except since I'm cut off near the boundary, I have to sort of go out, okay, in order to be a Hamiltonian flow. Okay, so questions about the definition? So there's this thing. Let me state a theorem about it. So let's say I have x and y an inclusion of Liouville sectors. Okay, so what's an inclusion? It's it's a proper embedding, exact and conical at infinity. Okay, so an example of such an inclusion. I'll just draw the picture here. Okay, so let's say this is my sector. Okay, so I look at inclusions of this form. Okay, so if I have an inclusion of Liouville sectors, I get a push-forward map on wrapped Floer homology. So on the wrapped Fukaya category. Maybe it's worth contrasting this to Viterbo functoriality, where I get a pullback. So these are very different from Viterbo restriction functors. So that's the first thing to say. I'll just finish the statements and then make some remarks. This defines a pre-Cauchy structure. By that, all I mean is if I include twice, if I have a bigger thing and then a bigger thing, it's the same as if I went all the way from the small to the big. And sort of up to all the necessary coherences and whatever that you need to make that an actual statement. Maybe I'll finish stating all the technical things that we need to construct for phase one. So we can also define a group, a closed string group of a Liouville sector, which we call the symplectic cohomology of XREL boundary. Okay? And this is also, it also has some sort of pre-Cauchy structure. Okay, so this is, again, it's, well, I mean, I can say some words about what that is in a few minutes. Maybe I just want to indicate what the rest of the structure is first. So there's an open-closed map from the wrapped Fukaya category of a Liouville sector to the symplectic cohomology of a sector rel its boundary. And this is a morphism of pre-Cauchys. Okay, so it's, I can, well, it means that if I include x into y, I can either look at the map on Hochschild homologies and then go to symplectic cohomology, or go to symplectic cohomology and then go to symplectic cohomology. They're the same. Okay, so this is the sort of structure that helps you put together a local to global argument. Let me maybe make some remarks about what goes into some of this structure. Yes,
In your example where you create a sector by cutting out the neighborhood of the stop,
yes.
is the function of your insisting that the Hamiltonians vanish at the new boundary recreating the definition of partially wrapped blood model in the presence of the stop?
Yes, that's what we believe.
And in that case, if you then include your sector just into the thing without stops, that's the same as Zach's inclusion function?
Yes, no, that definitely is the case. There's I don't think, so we've been talking with Zach about this, and I don't think there's, the devil's in the details somehow because the technical setups are completely different. And here you're, in the stopped wrapped Floer homology, you look at some quadratic Hamiltonian with a special, of a special form. And here you look at Hamiltonians that are cut off linear and take some limit. So but you would expect. Yeah. Okay, so remarks. Maybe I should say that Floer theory on Liouville sectors is mostly not so bad, but there's, as usual, whenever you're working on a non-compact symplectic manifold, you have to worry about things going, or a manifold with boundary, you have to worry about things going to the boundary or to infinity, right? So there's a new direction to worry about, which is things going to the boundary. Okay, so we have to worry. Okay, similarly, if you accept that, that one can define this thing, you might worry about how you define a co-restriction map. Okay, so similarly, it's easier so if you have x and y, I can look at the wrapped Fukaya category of y, where I look at objects supported in x, where I only do wrappings in x. Okay? But I allow disks to map into y. Okay? And it's easy to see that this thing, by sort of usual acceleration type idea is just wrapping more. This thing naturally maps to the wrapped Fukaya category of y. What you need to show is that if your Lagrangians are in x and you're wrapping in x but counting disks in y, that actually is counting disks in x. Right? So there's something to say there. Okay, so I might say there are two reasons why you can make all of this work, at least from our point of view. One is that, you could worry about disks going to the boundary of x, and then perform a next stretch and see what happens in the limit. Okay, so now it turns out that the condition we imposed on the Liouville sector structure implies that the characteristic foliation on the boundary of x has no orbits. In fact, it's just sort of has no closed orbits. Thank you. Yes, absolutely. So it's flow by this characteristic foliation is an R action. Okay, so if you have no orbits and you and you apply an SFT stretch to see what might happen if things go to the boundary, they'd have to break along an orbit, but there's no orbit to break along. Okay, so therefore, in some limit, they stay inside. Okay, okay. So that's I would say a good moral reason, and maybe two. You can actually build local maps to C from a neighborhood of the boundary. okay, which serve as barriers. Okay. So more directly, if you have a local map to C, you can project to C and argue that there's some barrier in C that your curve can't cross, and that gives you control over where your curve lies and upstairs. Okay, so say some words about what the relative symplectic cohomology is. Well, it's, again, some direct limit of Floer cohomologies now, closed-string Floer cohomologies of Hamiltonians, where instead of looking at Hamiltonians that are now 0 on the boundary, you look at Hamiltonians that are slightly negative. So here's a picture. So where the gradient of H looks like this. So it's slightly inward pointing along the boundary of X. And outward pointing in some large way along the boundary at infinity, and you take some direct limit as you increase the amount of outward pointing up here. So what this thing is doing is it's picking up orbits on the boundary and working rel the cohomology of this boundary of the sector. Okay, so here's a definition. We say a Liouville sector X has enough Lagrangians if this open-closed map is an isomorphism. So just remember, when there's a boundary, this thing doesn't have a unit. So this is sort of some analog of hitting the unit that's convenient for our purposes. Okay, so this is what we mean by having enough Lagrangians, and maybe I want to point out this. In general, this is a difficult thing to check, but one of the advantages of Liouville sectors is if you cut up your Liouville domain into lots of Liouville sectors, sometimes this becomes completely topological. Okay, so for some Liouville sectors, actually it turns out that the symplectic cohomology of X-rel boundary is just the cohomology of X-rel boundary. So this is a property of there being no orbits, of the cutoff Reb flow. Okay, and so we call such a sector a fully stopped Liouville sector, and for a fully stopped Liouville sector, verifying this is easy. Okay, because in nice cases it just boils down to checking that you've hit some homology classes by homology classes of your Lagrangians. Okay, just boils down to having enough Lagrangians, and so what are some examples of fully stopped Liouville sectors? Well, I'll just give you one for now, and then in the last minute or two I'll give you another. So for instance, if I take the cotangent bundle of a ball, so I know I can decompose the cotangent bundle of any manifold into cotangent bundles of balls, but cotangent bundles of balls are fully stopped. Okay. So there are no interesting orbits of the rib flow at infinity. Okay, so that's what it means for a sector to have enough Lagrangians, and now the theorem, the generation theorem, is that if X admits a homological covering, by sectors X alpha, which each have enough Lagrangians, then X is generated by the image of objects in all of these. Okay, which by a theorem of Abu Zaid, we know to check that it suffices to check that some open closed map hits 1. Okay, so this is the theorem, and actually I want to claim that it's, once you've built all this structure, it's completely formal. So all of the work was in building the structure, and now there is in fact nothing to do. Okay. So here's a big diagram that just comes out of the pre-Cauchy structure. I have a morphism of open closed maps from all of my local sectors to the local symplectic cohomologies. And I can build some big complex with all the Hochschild homologies of all the sectors, and some big complex with all the symplectic cohomologies of all the sectors. And this thing maps to symplectic cohomology, and this thing maps to Hochschild homology. And this map hits 1 by being a homological covering. That's roughly what it means, except if I replace symplectic cohomologies by cohomologies, this thing hitting 1 is what it means to be a homological covering. This is an isomorphism. Okay, therefore, one is hit. Okay, so I have maybe a minute. Maybe I'll say one thing in words and return to cotangent bundles for my last minute. So one thing in words is that the next thing to do is you can take arboreal singularities, which is some class of singularities indexed by some combinatorial data, some trees, build sector structures on them, and check that they have enough Lagrangians. And it turns out that, you know, the picture that's appearing is that their categories seem to be really simple and related to module categories over the trees, and everything is very explicit, and they indeed seem to be fully stopped. The final thing I want to say is I just want to point out that actually this, you know, in a lot of proofs of hitting the unit, you have to compute this thing, this group, symplectic cohomology, and check that 1 is hit in this map. I want to claim that actually this thing does not compute that. This is actually something purely topological on this side. Okay, so for a cotangent bundle, let me just replace all my wrapped categories by path categories. And let me replace my local symplectic homologies by local loop space homologies. This is what the diagram looks like. Now, I just want to point out that if U alpha were balls, if I were covering by balls, the loop space homology of a ball is contractible. This is just K. Okay? So I'm taking some homotopy colimit of K's. Okay? So this has another name. It's called the homology of Q. And this map is the inclusion of constant loops. Okay, I'll stop there. Thanks.